Oh, hey. So, we've all heard of dams and windmills as alternative ways to produce electricity. But have you ever stopped and wondered how these things work? If not, I'm here to do the explaining for you. The underlying concept behind these things is known as electromagnetic induction. This is the process by which an electromotive force, or electricity, is induced within a coil when it interacts with a dynamic magnetic field. Allow me to demonstrate. Here's a copper coil wrapped around a plastic tube, and here's a very strong neodymium magnet. When the magnet is moving quickly inside of the plastic tube, electricity is being induced in the coil, as depicted by the lighting of the light bulb. But how does this work? Well, it all started in 1831, when Michael Faraday first discovered electromagnetic induction. It was already proven that inducing an electrical current into a coil would produce a magnetic field, which we know as an electromagnet. Faraday wondered if the opposite were also true. Would the presence of a magnetic field in a coil produce electricity? After a series of experiments, he concluded that any change in the magnetic environment of a coil of wire would cause a voltage to be induced in the coil. So let's break this down. The magnetic field is the visible area of effect of the magnet's attraction and can be depicted using vector lines as such. The magnetic flux is essentially a measurement of the magnetic field strength. It is how many of these magnetic field lines are passing through a particular surface. For example, there are more lines passing through a surface on this part of the magnetic field than through the same surface on this part, which explains the different forces of attraction in both areas. Going back to Faraday's law, it states that any change in the magnetic environment of a coil will cause electricity to be induced in it. Now, this change in the magnetic environment can occur several ways. In the following cases, the surface, which is the coil, is being exposed to different amounts of magnetic field lines over time, thus a changing magnetic flux. First of all, a magnet can be moved relative to a static or non-moving coil. Secondly, a coil can be moved relative to a static magnet. Thirdly, a coil moving in one direction can be exposed to a magnet moving in the other. However, electricity will not be induced in a static coil exposed to a static magnet. Or in a moving coil exposed to a moving magnet at the same velocity. This is because in both cases, the magnetic environment in and around the coil isn't changing. The magnetic flux relative to the coil is neither increasing nor decreasing. How much electricity that is produced depends on the strength of the magnet, the rate of change of the magnetic field, and the number of turns in the coil.